graph represents the graph of acceleration versus time for an elevator moving vertically. Two students discuss the velocity of the elevator while the acceleration is not zero. So even before you read these claims, let's take a look at the graph and interpret it for ourselves. Because sometimes after you read what somebody else thinks, it tends to sway our thinking. So I'm going to cover that up, and I'm just going to take a look. This axis is acceleration, so the values are the acceleration. So positive values of acceleration are up here, and the negative values of acceleration are down there. The area of an acceleration time graph is the change in velocity. But we don't know anything else other than that. So here we've got an acceleration equals 0. Now we know that acceleration equal to 0 could be either at rest or constant speed. So that we know. This has a value of positive 4 meters per second squared. So that we know that, we don't know much else here yet. And then this again, acceleration equals 0, so we're either at rest or constant speed. And here we've got an acceleration of negative 4 meters per second squared. So all that we know is an elevator is moving vertically. So that's it, okay? We don't know anything else. Student 1 claims, I think the elevator is moving upward during 5 to 10 seconds and downward during 15 to 20 seconds. Student 2 claims it's possible that the elevator changes direction from 5 to 10 seconds. Can student 1 be proven wrong? Well, if that student is correct, if the elevator is moving up, it would have a positive velocity. And during this time period, then it would also have a positive acceleration. But it could be that the object is moving down and has a positive velocity and has a positive acceleration. So the difference is that this is increasing speed, this is decreasing speed. Is that possible? Sure. But can you prove this guy wrong? Well, no, because if the object starts at rest, he could be increasing speed. But if this portion means that he's going at constant speed, then he could be moving with decreasing speed. So you can't prove him wrong. You can only validate that it's a possibility. So what this guy says, that it's possible that he changes direction during this time. Well, is that possible? Is there a situation where your acceleration continues to be a positive value even though you've changed direction? Well, if you're at constant speed here and constant speed here, could you have switched direction in between? I'm trying to think of a good example. So if you're moving in this direction, let's say you have a negative velocity. Well, this is an elevator, so it's not going to be, let's pretend it's moving down. So I'm going to work over here. If it's moving down and it's slowed down, so the acceleration would be positive. Then, right, if the acceleration stayed positive at the same value, but it started to move upward again, it could then increase speed upward. So it could change direction while the acceleration changed. There's nothing on this graph that would have to change otherwise. So either of these guys could be right. Number 2, the graph to the right shows the acceleration versus time graph for a car moving in a straight line. At time t equals 0, the car is moving at 10 meters per second. So at this point, velocity is 10 meters per second in the positive direction. At what time after t2 does the car again move at positive 10 meters per second? So what we're looking at is when is the change in velocity 0? And I know that the area of an AT graph is the change in velocity. So I'm trying to find out when's the change in velocity 0, when's the area add up to 0. So if the area here is 2 times 2, which is 4, then there is no area here. Then I'm looking, when is this going to be negative 4? So if this is negative 2 down and you go for 2 seconds, then at 6 seconds, is the place when you're going to be back at the same speed. Number 3, consider the following graphs noting the axis. Which of these represent motion at constant velocity? So they're all different axes, right? So is this constant velocity? Well, the slope of a position time graph is velocity. So if there's a constant slope, then there's a constant speed. So definitely that one. This one is a velocity time graph. So this shows zero velocity. This shows a bigger one, bigger, bigger. So this is showing an increasing velocity. This has the same value for velocity at every time period. So this is constant velocity. This shows a changing acceleration, which means that velocity is definitely not staying the same. This shows a constant acceleration, which means that velocity must be changing. Remember, the area is the change in velocity, right? So therefore, there is definitely a change in velocity, so it cannot be constant. This velocity versus time graph, we're going to translate this into a position time and an acceleration versus time graph. This is really good to practice, making this kind of transference of the representation. So we're going to first interpret this, and then we'll see how we can move that information in here. So this didn't photocopy very well, so let's just get this going. At 1 second here, it's going 1 meter per second, and at 2 seconds, it's still going 1 meter per second. So this part is constant speed. This is increasing speed, right? Because this is velocity. It's going from 0 to 0.5 to 1. Then it suddenly drops, and the velocity here at 2 seconds is negative 0.5. So the sudden change here, and it stays at negative 0.5 for until 3 seconds. So again, this is constant but negative. This is constant but positive. And then it drops, the graph drops again to an even bigger velocity. So at 3 seconds, we're moving at negative 1 meter per second, and that's going to last up until 6 seconds. So this is constant and negative again. So that's what's going on here. So we can take this velocity time graph and we can get position from it by using the area. So the areas here, right, are going to give us our displacement. So this is going to be 1/2 times 1 times 1, which is 0.5. So that's the displacement. And then this one is going to be 1 meter per second by 1 second. So the area is 1. This is negative 0.5 by 1 second. So this is negative 0.5 is the area. Then this whole thing, right, this big chunk here, this is a lot of displacement, well, relatively speaking. It's a big rectangle. It's 1 second by 3 seconds. So this is 3 meters, right? So these are all distances in these circles. So that enables me to draw my position time graph. So I'm going to take that information and I'm going to make a position time graph. So this is my position and here's my time. And I'll set up my 6 seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so we have to do it in ones. So there's 5 and there's 10. And then we need 0.5 plus 1 minus 5. So that's 1, and this is negative 3. So we actually need to go up to 1.5. So we'll say 1, 2, 3, 4, 5. So at 1 second, we're at 0.5. At 2 seconds, yes, that's right. And then at 2 seconds, we've gone 1.5. So by the time we get to 2 seconds, we're at 1.5. And then we go backwards, and we're at negative point. We've gone backwards negative a half, and that's at 3 seconds. And then at 4, so for over the next 3 seconds until you get to 6 here, we're going to go back down -3. So 1, 2, and 3. We're going to go under here to -1. So what are the shapes of this graph, of these pieces, these segments? So this is increasing speed, so it's a curve. This piece is constant, so it's a straight line. This piece is constant with a negative slope, and this piece is constant with a negative slope as well. And that's it for that one. All right, let's try, let's do the acceleration time. So acceleration time is the slope of a velocity time graph. So these slopes are what we need. So the slope here is going to be, right, change in y over change in x. So we're going to get 1 minus 0, 1 minus 0, so the slope is 1. And that's going to be your acceleration. This is constant speed, so acceleration is 0. Here acceleration is 0, and here acceleration is 0. So making the same axes here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This is time. This is now going to be acceleration. And we can do, here's 1, 2. So we're going to have that first, for that first second only, we're going to have an acceleration of 1, and that's going to be a constant acceleration, so it's a horizontal line, because it's not changed. The slope doesn't change, the acceleration doesn't change. Then it's going to drop, and it's just going to stay at 0 for the whole rest of the time. That's it. That's all you got to do. Okay, so let's look at the next one. Consider a person playing on a trampoline. Let t equal 0 as the person reaches the highest point of a particular jump from the trampoline. From this point on, the person simply stands straight without bending legs and falls onto the trampoline and rebounds into the air. So I'm trying to visualize this. So you're at the highest point. Here's the trampoline here. So let's assume that this is the height, the y position. And we're saying this is t equals 0 and v equals 0. She's just kind of hanging out there, and then she falls down. She hits the surface of the trampoline, right? So that'll be like v1, right? Contacting the trampoline. So this is time is 0.5 seconds. And then in the next stage, she sinks into the trampoline. So t2 is going to be 0.8 seconds, right? So it's in contact, going down, and rises from 0.8 all the way back up to 1.2. So it gets back up here. Oh no, sorry, so I have to fix that. Let me fix this. Call this T4 equals 1.2 seconds. The 0.8 is when she's rising back. That's the limit, right? She ends up back off of the trampoline. This T2, this bottom value here, is when she's at rest for a split second, right? We don't know what that time is, but we know that that's 0. At V3, when she's just leaving the trampoline, she's at some maximum speed. At V4, you're back at rest again. So this is the cycle. I'm sorry that's so messy, but you have to kind of think through the cycle. We have starting at rest, falling to max speed, hitting the trampoline, sinking down, coming to rest, being pushed back up, and then leaving the trampoline and going back up to max height. So when you're going to draw a position versus time graph, right? So we've got a total of 1.2 seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll do 1 second. So we'll do 0.5 seconds, and then we'll do 1, 2, 3. Here's 1 second, and then that'll give us another 0.25. Okay, so every 2 is 0.25. Okay. In terms of the height, we don't know any distances. So at the beginning, we're at maximum height. So let's just make up a number. Let's just do it right here. Here's our max height. We'll call it Y max. That's the beginning. And that's going to last, right? She's going to fall down until she gets to 0.5 seconds. So here's 0.5 seconds, right? When she's right above the, the surface of the trampoline. This is going to be increasing speed in the negative direction. Okay, that's what increasing speed, right? The slope gets bigger in the negative direction. You're accelerating down, right, due to gravity. So you have to have that curve. Then the trampoline slows the person down, right? And then they're going to speed back up again. And that lasts until about 0.8. So back here is when she's back up at the same position. We don't have a number for that, but this is our surface of trampoline is right there. So this is going to slow down to rest and increase back again. So you're back at that max velocity. And then as she rises to that maximum position again, she's going to slow down. So it's going to curve back down, but in the positive direction again, right? You're moving up, but you're slowing down. That's what that looks like. All right, so let's look at the velocity time graph. So since we have changing velocity in changing direction, we really need to make sure we have a positive and a negative region for our velocity. And here's time. So again, we can do 1, 2, 3, 4. We'll call that 0.5, 0.25, 0.75, 1, and here's like 1.2, which is what we need. So we said that she starts at rest. Let me use a highlighter. I think it'll be easier to see. So she starts at rest here. And then at 0.5, she's at a maximum speed. We'll just put that here. I don't know what that is. Oh, but I made a mistake because this is positive Vmax. We're actually going to be going in the negative direction at first. So this is negative Vmax. So we're going to put that down here at 0.5 seconds. She comes back down to rest somewhere in the middle and then gets back up to this Vmax right at the surface of the trampoline. Okay. Then she's going to slow back down until she gets back down to 0. So the line is going to look like this, right? She's going to increase due to gravity, so it increases at a steady rate. Then a trampoline doesn't act so steadily, but we'll assume that it's a steady acceleration, and then it decreases again, back down to 0. And the last one then is going to be our acceleration versus time graph. So first draw the axes. So this is acceleration and this is time. And you'll notice, when we don't have numbers, it's not important to put them, but when you know something, you should put something down. Okay, so we've got those axes, and then on the acceleration, well, we do know some of it. We know the acceleration on when she's in free fall. Well, you may not know that, but acceleration while she's falling is -10. So we can actually put that on our scale. We'll put it's 9.8, but it's fine. -10 meters per second squared. So let's examine this part while she's on the trampoline itself. While she's moving down, she's moving in the negative direction, decreasing her speed, so acceleration is positive. Then when she reaches rest, then she's going to be moving back up and increasing her speed, so acceleration is positive. So thinking that part through is really useful. And you'll notice I always rely on these motion diagrams. I find them to be one of the best tools for figuring that stuff out. I hate figuring things out in my head. I just can't do it. So during the free fall part, up until 0.5 seconds, she's got a constant acceleration due to gravity. And then after, at that 0.8 seconds, she's also got that same value when she's free falling on the way up. And then there's some positive acceleration due to the trampoline during that segment in between. And you can, if you can't reason that out using your motion diagrams, look at your VT graph. Remember, the slope is your acceleration. So notice this is a straight line with a positive slope, so you have to have some positive value. So I'm just going to call this positive acceleration of the trampoline. That's it.